Good afternoon from my side. This is Hani Abdurrahman, and today I'm going to discuss for you the paper that I have been assigned, which is related to a dynamic world near real-time global 10-meter land using land cover mapping. I have a bit of sore throat, but I'll try to be as much as clear as I can. Firstly, this paper was really relevant to our project because our project involves using geospatial data to monitor deforestation near real time. So it covered most of the aspects that we will actually really need to implement within our project, though there are, of course, a lot of technical things that are involved. Firstly, I'm going to address the aspect of data collection and pre-processing. Uh, for data collection, for the model was trained to train on dataset collection using what you call semi-supervised deep learning. This was already this concept has already been discussed by Mr. Emma in his previous lecture. Semi-supervised deep learning means it involves both aspects of semi-supervised learning and deep learning. So you integrate them together. Semi-supervised learning, it uses some aspects of labeled and unlabeled data. Deep learning means that it uses deep neural networks, so it to make complex decision making to imitate the human brain. So, firstly, following that, we talk about labeled box drawing tool, which has been used by experts in order to map the features. So this is how we actually managed to label the data. There were a group of experts that would pick tiles of satellite images, and then we would map those images, and then would like, this is now the shrubs, these are the crops, this is the river, this is the lake, this is the forest, and so that was the kind of label data that you have been using. So image pre-processing is also involved. So remember, the satellites we have levels. There's like level 2A, level 2B, 1A, 1C. So all those levels within the satellites have pick images of different wavelengths, some of different infrared waves, lengths. So combining all those different ones can enable you to like process this image. So it involved dynamic land use, land cover annotation, using both supervised and unsupervised learning. And and of course, this will involve convolution neural networks, because we need to process these images that come from a satellite. And convolutional neural networks that's what it is, image processing. Now, real time inference. So the fact of the matter is, we could not achieve 100% real time real time monitoring. However, we can achieve near real time monitoring uh, through the use of Earth Engine and Google and the cloud AI platforms, which really help us in order to attain near real time datasets. However, uh, this still does not guarantee a much faster rate of attaining data. Uh, every time an image is taken from different areas, it has to take at least 40 seconds to be processed by the dynamic world engine. Technical validation. So just like I've said, we had a group of 25 experts within this paper that have been involved in labeling the data on the Sentinel image tiles. So they would label the data, then they would again go and train about 35 non-experts to now further go and create more labeled data from other tiles. Because the Earth is a big globe, so it's just not there's just the enough experts to do all the work. So they had to now also train non-experts to to uh, to improve on the work output. So the expert and non-expert results were compared in order to improve accuracy and and correctness. So as you can see, we used various voting mechanisms for validation, and they also did what we call per pixel confusion matrices, are presenting comparing the non-experts and expert consensus. Basically, just involve this just all talks about how the experts had to now train the experts. Now moving on, this is now how the non-experts have been taken through the trial that they have. As you can see there's like mottled areas of water. This represents flooded vegetation because you can see there's some darkness there. It means this, something like a swamp or something like a what is something called like a mangrove vegetation. And then and then there's an area where which is like kind of brownish at the same time, kind of darkish, which is now the river. And so they used various tiles in order to train these non-experts, and these non-experts would then further go and now do the labeling by themselves. The area of white you can see are the buildings, and so it didn't involve a lot of problems to teach them. However, still, yeah, uh, there have been challenges differentiating some land cut types. So as you can see there from this image here, they all these two images show image tiles that have been annotated. The one above has been annotated by experts. As you can see, they haven't done a lot of work. But when you look at the one that has been covered now by the non-experts, you can see that they have covered a lot of areas, going to about count of 60 hexagons. And mind you, each hexagon represents 58,000 kilometers squared. So they did labeling of 58,000 kilometers squared area. So, well, now the question comes: Are what the experts labeling correct? It has been shown that there's the correlation between the dynamic world results and expert labels is about 73.8%. So which is a fairly good number for them. Now, how about we compare now the dynamic world results? Is the dynamic world result the standard? Should we set it as the standard for what we need to really achieve? And dynamic world has really met the standards, and it is compared with the existing global and regional land use land cover datasets, it actually showed high agreement, which means that it's giving us good results, and to some extent it even exceeds the ones that are already there. Well, just like I had said, some areas like the rivers and the forests are easy to label, but there are areas such as the crops and the shrubs, which have been a challenge for both the experts and non-experts to label, as well as the flooded vegetation, because you could confuse the vegetation with actually the rivers. Okay, and of course we had some they had some challenges and uncertainties in developing the existing model. Just like I've said, distinguishing the different biomes, the shrublands and the crops, and then remember the aspect of clouds covering the vegetation. Well, code of the dataset is available as in Earth Engine image collection. Well, but accessing the dynamic world dataset has been actually a challenge for us. So we, as a power group, we are relying on other datasets for this. The training model, inference code, and additional information on image are archived for reproducibility. User notes and conclusion. Firstly, just like I said, this work will involve us using convolutional neural networks and recurrent neural network, because remember, images will have to be continuously monitored over a period of time to detect for changes. So this is now where the recurrent neural network will be involved, and then convolutional neural network, because of course we need to process the images, identify the different land cover types, monitor them over a period of time. In this case, we are monitoring. Uh, in this paper, they are monitoring at a resolution of 10 meters. So any change that occurs over a distance of 10 meters using the Sentinel-2 different layers of satellites, then they are they are actually able to detect these changes within their model. However, just like most machine learning models, it is 100% accuracy is never guaranteed, and so is the case for this one right here. Cloud shadows. Now we have cloud shadows that are there. We have some areas which have dense clouds, and then augmentation as well, because maybe we don't have enough data set from a particular area. All affect the accuracy of our results and accuracy of our model. Well, basically, these are some of the